And let's see. So we're just going to start with integrals now. Okay. What's the idea of integrals? The idea is that in common terms, just if we were to explain it, no theory, no nothing, it would just be the inverse of derivation. Okay. And I'm just gonna draw it. So for example, if I'm going from x squared to 2x, this is derivation. Okay. And if I'm going the opposite way, this is integration. Okay. Now, I'm going to give you the full definition, or again, it's basically just what I said, just written nicer. And then we are going to, I'm just going to show you some properties and yeah, show some exercise along the way. That's kind of the plan for today. So the definition is, or I think it sounded like this. Definition is, if f prime of x is equal to small f of x, then integral of small f of x dx, I'll explain, is big F of x plus c. Now, let me elaborate. Let me explain. This snaky S looking sign, that's the integral sign. Okay. I've seen a lot of people doing multiple ways. I don't care. As long as it looks like something like this, I will be happy with it. D of x basically shows you which variable you're integrating over. Okay. So in my case, d of x, f of x. I'll show you an example where I might have something else, but I need to look at d of x to tell me what variable I'm integrating with. So if you want to just write it as shows what variable I am integrating over. Okay. F of x, and c, this is a constant, any constant. Okay. Why is it any constant? Well, it all comes back from this idea over here, right? For me to get 2x, I can, if I take a derivative of x squared plus 5, or I take a derivative of x squared plus 47.51 dx, I still get 2x because the constant vanishes. Okay. But in order to be complete, and it's actually going to matter in the future, in some future cases, you have to put the constant always. Never forget it. When the integral is like this, which is called an indefinite integral. Oh, sorry, no, it's not indefinite. Sorry about that. If I'm doing some simple math mistakes or something like that, just I'm a little bit sick, so let it slide, please. It's I think it is indefinite, but I'm just losing my head. If you have an integral, just always write the constant at the end. Okay. Now let's take some examples. Okay, so let's just see how it works in very simple terms. What's integral of 5, for example? And before I give you some. Also, I'll give you some properties and some theorems, but realistically, if you're very confident on derivation, then integration is going to be very easy for you. So when I say integral of 5 dx, I'm basically asking you, what if I take a derivative gives me 5? Exactly. And the answer here is just 5x plus a constant. Right? So now let's take I'm just going to do some examples, and then I'm going to show you the properties and show you that basically with what we've done here, we've basically just used all the properties. They're very, very intuitive, the properties that I'm going to show you. And the whole idea is to know derivatives very, very well. So what's the derivative of 2x plus 1 dx? Again, what if I take a derivative of gives me 2x plus 1? That's what should be going through your head every time you're doing integrals. Now, at some point, you're probably gonna pilot into some properties and whatnot, but this should always be in the back of your head, because at some point after you do enough integrals, you don't actually need to do all the math again. Okay, you just see it. So in this case, what? Any ideas? What if I take a derivative of gives me 2x plus 1? Yeah, exactly. Exactly. Right. So as I said, if you're confident with taking derivatives, integrals are actually very, very easy. Now, are all integrals going to be as nice as this? Definitely not. But it's a good step. Now, let me start with the big properties. Just a disclaimer, for those of you that are not really confident in derivation and think I'm going to give some magical properties here that are going to solve integration, that's not going to happen. There's no replacement for actually knowing derivatives. Okay, so let me just erase this. Let's see what we can do. Okay, so first one is integral of a constant times f of x dx is equal to the constant times integral f of x dx. Well, seems intuitive to everyone. Remember how when you had those ugly functions and you were taking derivative of 27x squared minus parentheses minus x to the third, something like that, dx. When you had something like this, remember where you just took the 27 in front? Okay, same concept applies here. You can just take the constants in front of the integral, They're not going to affect your final result. Now, integral of 0 dx. What is integral of 0? It's not 0. It's 0 plus a constant. If I take a derivative of any constant, I'm going to get 0. Okay. Integral of f of x plus g of x dx. So if I have two functions, like we had the previous one, well, I gave you 2x plus 1. I'm pretty sure the person who did it just in their head just split it into 2 and thought. So my example, I think, was 2x plus 1. And I'm pretty sure the person just thought, okay, what derivative gives me this? What derivative gives me this? Okay? That's the whole idea here. If you have integral of a sum of functions, you can just split it up. It's equal to integral f of x dx plus integral g of x dx. Okay. Cool. Now, let's give some more. These are more conceptual. Let's give some more actual hands-on math formulas, okay? Which are basically just going to be the inverse of integrals, so the inverse of derivations. Remember we had the cheat sheet for all derivation formulas? I'm basically just going to do the exact same thing here, but the opposite way around. So you had, I think the first thing you learned how to take a derivative of, or one of the first things, was the power, right? Derivative of x to the power of n dx is n xn minus 1. Right? Everyone, I think, did this. Now, for integrals is, okay, if I have integral of xn dx, it's just the opposite way around. So it's just x n plus 1, n plus 1, plus a constant. Okay, makes sense. Makes sense for everyone. Again, whenever, and if I might be wrong. That's why I'm asking you several times. I'm not checking or anything. Yeah, the whole idea. Whenever you're in doubt if something's wrong, if you wrote an integral and you're in doubt if something's wrong, what you can do is you can just check it. Okay, if I take a derivative of this, do I get this? And if the answer is yes, then the integral is correct.
I don't understand why they didn't n plus 100.
Well, let's see. Great question. Let's see. Maybe I'm wrong. Who knows? As I said, my brain isn't working at full capacity, so I'm trying. But let's see. So if I have xn plus 1 over n plus 1. Okay, let's take it without. So again, as I said, if you want to check, you just take the derivative of the right-hand side, and you see if it's equal to this. So xn plus x, I got a question in which they asked me, why do I get this? So I'm basically just, all right, let's play devil's advocate. Let's see, maybe the person's right. So x to the n plus 1 plus a constant derivative of x. I want to get xn, x to the power of n. But if I take derivative, I'm just going to get n plus 1 times xn. Okay? So the reason I put xn plus 1 is so that it goes away and I get exactly xn. So again, for those that didn't follow, if I don't have this xn plus 1, if I don't have this n plus 1 here, then when I take a derivative of the right-hand side, I'm just going to get n plus 1 times xn. But I'm not integrating this. I'm integrating xn only. Okay, did everyone follow that? Make sense for everyone? Okay. Now, sorry if I'm making stops. My throat just is killing me. Okay. Now, before we move on to the next, I guess, semi-properties, does anyone see something here that doesn't make sense, like a little bit sketchy? It's more of a fine observation here in regards to what I wrote here. It's not wrong, but there is a case where it becomes a little bit sketchy. Can anyone see it? I missed it. I missed the 9. Yeah.
And make this minus 1.
Exactly. If it's -1, then I would get 0. Then I would get 0 there, which doesn't make sense. So that's a great observation. So so this formula is correct for any n not equal to -1. And for any formula not equal to -1, it's perfectly fine. But for -1, when I'm basically integrating 1 over x dx, again, this is just x to the power of -1. Okay. What is this? What is this integral? What if you take a derivative of gives you 1 over x? Yeah, close. It's ln absolute value of x. Okay. Because 1 over x can be negative. I can have 1 over -10 or 1 over 10, but ln cannot be negative. So I need to put an absolute value. Cool. I don't know really what other properties I can give you. I guess I can just show you an example of e to the power of x or something like that. But other than that, there's not much I can show you here. If you're right, all these formulas just come more or less naturally, I guess, once you know the derivation. But let's just show e of x, and then I'll just do some examples. So integral of e to x dx. What is this? Yeah, it's e to dx. This is why e to dx is such a special thing in math, because whether you integrate it or derivate it, it just never goes away. It just stays exactly the same. The proof why it stays exactly the same is probably not something you're going to do in this class. But if you have e to the ax dx, what is this equal to? It's just eax, and when I take a derivative of this, I know there's going to be an extra a, so I want to get rid of that a. Plus a constant. Okay. Now, I think there's not much more really I can show you on these indefinite integrals. So let's just take an example, and I'll give you probably 2 minutes to solve. I think 1 minute is enough, actually. 1 minute to solve it, and then we'll see where we're at. So let's just do this. I wrote all the properties there, and when I'm going to solve it, I'm actually going to tell you at each point what property I'm using. It might, for some of you, it might be quite obvious, but it creates a good habit. When things get really complicated, it creates a habit. So let's just take 47x to the third plus 25e to 6x plus 5 plus 2 2.1x dx. Well, I think 1 minute should be fine. All right, guys. So did it work out? Did we do it? I hope so. So the first step I would do personally here, I don't know how you guys did it. So obviously, so let's get it straight out. If you're confident in what you're doing, if from here you just literally write me the answer, I'm perfectly fine with it. Since this is the first time some of you or most of you are seeing integrals, I'm gonna do it in multiple steps. But if you're on you're on an exam and you have something like this, and the next line is actually the answer, I have nothing against that. So you don't need to go for the extra steps if you don't need to. Okay? But since it's the first time, my approach would be to just split it. Okay, so I'm just gonna split it into 4 mini integrals that I'm gonna solve. So I'm just gonna write it as integral 47 x to the third dx plus integral of 25 e6x dx plus integral of 5 dx plus integral of 21 x dx. This would be my first step. Okay, now, so my first step, I have the splitting thing, the f of gx, the integral of f of x plus gx. That's what I used here. Now, the second one I would use is I would probably just take the constants out for now. At this stage, for what you know, I think the best step would just be to take the constants out. So I'm going to move this out here. I'm not going to rewrite it again, but I'm just showing you what I'm doing. Taking the 25 out. This 5 doesn't really matter. Okay, everyone on board? Makes sense for everyone? Now, I just literally plug in the formulas. And I would get 47 times, this is x to the 4th over 4. And I know somebody's gonna say it, so I'm gonna talk about it immediately after I finish writing everything. 25 times, this is e to the 6x over 6 plus 5x plus 21 times x over 2. Okay. Now, what am I missing? So all the math I just replaced using the formulas. What am I missing? Yeah.
Also an x squared over 2.
Oh, I put x over 2. Yeah, there's an x squared. No. Yeah, this we blame it on a typo. I specifically forgot something. The c, the constant. Great. Now, I'm asking you guys, should I put a constant for each of these integrals? So I'll just have c1 times 47, c2 times 25. You get, should I just do that? Or should I just put a c here? Yeah.
Just see at the end.
Exactly. Right. It doesn't matter. It doesn't. So the whole idea is when you're summing up multiple integrals, multiple indefinite integrals, you don't need to carry the c's with you all the time. You can just do the whole formula and then put a c at the end. Because realistically, let's think about it. If I give you a constant, okay? I give you a constant, any constant I want, and I tell you to multiply it with 47. That still makes it equal to any constant in the world. So it doesn't matter. Okay, so if you were to write it here, let's hypothetically, don't do this, but hypothetically, you would just do 47 C1 plus 25 C2 plus 5 C3 plus 21 C4, whatever. Like I just wrote all of this thing. This is basically saying that you can get any value, any constant. So why bother in doing all of this and just not do this? Okay, so makes perfect sense. But I just wanted to get your attention on this because I've seen in the past years people carrying multiple C's across, and it gets very confusing for me, really. So yeah, just don't bother, but don't bother carrying the C's, but don't actually ever forget the C at the end. Okay, now the time, yeah, I will introduce definite integrals. I will give a short, let's say, view into how to get the proof for the solution, for the value of it, but don't feel obliged to remember the proof or anything like that. So, definite integrals. They look exactly the same. They compute almost exactly the same. There's only one big difference between them. The fact that they have these two values, which translate into integral from a to b of f of x dx. Okay, that's how you read this. Previously, I would just read it as integral of f of x dx. Now I just read it integral of f of x dx from a to b. Okay. Now, this, luckily for you, actually has a representation that, yeah. Yeah, so you meaning, can I just? On the other cases? Yeah. Yeah, I can still do that. So I was gonna say, yeah. Good question, yeah, but a little bit ahead of me. But yeah, all the properties, mostly all the properties are gonna stay exactly the same. It's still the same idea. Now, this actually has an interpretation. If this is your graph, and this is your f of x, this is a, this is b, this is f of a, f of b, then integral from a to b of f of x dx is this area. Okay, that's why integrals are quotations mark area under the graph. Okay, so that's the idea. Again, area under the graph only for definite integrals. For indefinite integrals, or the ones that didn't have this a to b thing, right, since I don't have the edges, I don't have a to b, the graph can just go forever, so it doesn't make sense. Now, I'm going to show you the exact solution of it, and then I'm gonna spend maybe 2 minutes, not more, on basically showing you how to get the solution of it. But I don't even know I don't think you know the theorems necessarily for that, but let's leave it at that. So if, again, if big F of x is equal to derivative is equal to small f of x, okay? In this case, there's actually a term for this f of x. This f of x is called primitive. Of small f. I'm not really a big guy for names, so if you don't want to remember this, no, I'm not really stressed about it. Okay, it's called a primitive. I've heard in some literatures being called antiderivative, which is antiderivative, which, you know, is kind of intuitive. If f of small f is the derivative of big F, then big F is the antiderivative of small f. So it kind of makes sense. But if big F derived the small f, and or if you want to phrase it in words, if big F is the primitive or antiderivative of small f, then integral from a to b of small f of x dx is equal to big F of b minus big F of a. And this is the thing you're going to use in all integrals from now. That is actually very important. Okay. Now, I'm just gonna, before we actually go into the proof, so I think we're actually close to a break, and I kind of need a little bit of a break for my neck. So for those, I'm asking for just sort of proof basically of this. That's the only reason I'm asking. Does this thing, this phrasing, look familiar to any theorem you know? Yes or no? Well, so I think since I firmly believe that more than 70 to 80% of the class, if not more, are not interested in the proof of this, because you're never going to have to prove this. Let's agree. You're never going to have to prove this in this class. I think we should take a 15-minute break now. And if you're actually interested in seeing or me showing you how to get this, I would be more than happy to show you in writing. Okay? So let's take a 15-minute break now. And then we're going to work more with these things. Okay, guys. So now let's talk about some I guess mini properties of this, and then let's move on. So first of all the properties, everything that I showed you for indefinite works for definite. For the previous case, indefinite works for this as well. Like, and you can split them, you can move the constant out. Everything that I showed you still works here. Okay. Now, so the only properties that I can show you here is in regards to this A and B situation over here. So let me ask you something. All the properties I'm going to give you right now are intuitive and just meant to basically just fool you around. What is integral of A to A of f of x dx? Yep. I should have asked that before writing this formula. Yeah, it's 0. So it's either you use the formula, which is fair, or you just think according to the graph, right? I'm interested if this is my f function. This is A, this is B. I'm interested in this area over here. If the sides are the same, so if I'm basically just one line, there's no area there. That area is 0. Okay. So this is correct. Now, in this drawing and everything I've done up to this point, I've assumed that B is greater than A, right? Like I've put B on this side, I've assumed that. So I'm asking you, would it be wrong to just write, integral from 1 to 0 of f of x? Would this be wrong? Would this make sense to you guys? Does it make sense? Okay, so I see everyone is lost. So the answer is that this is not wrong. But two ways. You either just two ways. You either just look at the drawing and think like, okay, if it's like this, so if B is greater than A, and I'm integrating from, let's just use that example. So let's just put this 1, 2. So 2, 1. Okay, if I'm integrating from 1 to 2, so I'm moving that way, that this area is positive. If I'm moving this way from 2 to 1, it's negative. So it's not wrong. It's just minus integral 1 to 2 f of x dx. So you can flip the heads of integration. The general property is this: integral from a to b f of x dx is just equal to minus integral from b to a f of x dx. Okay. Now, one other cool thing that you can do with these definite integrals is you can split them in another way. So in the indefinite case, I showed you that we can just split them according to formulas, right? If you have multiple things inside, x squared, x to the third, etc., you can just split them and compute them as different integrals. In this case, I can split them in a more interesting way. So I have integral from a to b f of x dx. I can split it as integral from a to c f of x dx plus integral c to b f of x dx. This should make sense intuitively, right? Because if this is my graph, this is the thing I want to draw. This is A, this is B, this is C, this is B. If I'm interested in the area between A and B, that's what I want to compute with the integral, the area from A to B. So I don't have multiple colors here, but I want to compute this whole thing with my integral. It's the same as computing the first part of the integral, this, and then computing the second part. Right? Basically. So they're quite intuitive. Now, what's the main difference outside of the fact that these definite integrals have some things over here? What's the main difference that you have not seen in any of the formulas as opposed to the indefinite integral, the first case?
It's a constant.
There is no constant here. Okay? There is no constant here. That's the whole idea, that the constant is only present in the indefinite integrals. And in the indefinite integrals, you're gonna get something like this: x squared plus x plus c. So something in terms of the variable and a constant. In the definite integrals, you are always supposed to get a number if everything is known. So let's take an example of that. Let's take a very, very simple example. What is integral of from 0 to 1 of x squared plus 2 dx? Okay, so I'm just gonna split it right now, see what I get. integral from 0 to 1 x squared dx plus integral 1 to 0 this is just equal to there now you cannot the notation is there's a certain notation here which is you write the primitive. This is again it's just a pure notation but it's very spread out. I think everyone does like this. What's the primitive or antiderivative or what do I need to take a derivative of to get x squared? I just showed you the formula and we did it before. It's just x free to the x to the third over 3, right? And I told you when you're doing definite integrals, do not write the constant. Okay, when definite, not write the constant. So the notation is you write the primitive. So I write x to the third over 3. And I say I'm gonna integrate it, so just a line from 0 to 1. And then I do what's here? What do I need to take a derivative in order to get 2x? So I get 2x from 1 to 0. From 0 to 1. So now what you do is you just replace them and you write them as 1 to the third over 3 minus 0 to the third over 3 plus 2 times 1 minus 2 times 0. This is just a fancy way of writing it, okay? This is basically f of 1 for this, and this is f of 0, okay, for this first integral. So that's where the formula comes from. But this is just a nice way of writing it. It just makes things very nice to write. Okay, now I'll just give you some examples because this is literally all there is for integrals. So we're just gonna do 2 more examples, then I'm gonna give you the roadmap. What we did today is 1/3 of everything you need to know about integrals. Yeah.
Can you explain again the notation of just the line?
Yeah, sure. I'm a little bit confused what exactly I can explain, but yeah, so when you have integral of f of x from a to b dx, I said and I stand by that it's f of b minus f of a. Now, if you can do it straight out, if you see that in your head, this is x to the third over 3, and you just automatically replace it with this, I have no problems with that. But if you don't, or if you want to do all the steps, how would you actually write this? What intermediate step would you write? So that's where the idea comes to just write it as f of x line from a to b, which is exactly what I did. I just wrote x to the third over 3 from 0 to 1. And then I plugged in the values. Okay? There's not much intuition or anything like it. It's just something that people write. Because otherwise you can't just every time. So when you're computing integral, especially towards the end, you're replacing so many of these integrals that you can't just, I'm gonna define f1 being x third over 3, f2 is equal to 2x. It just takes too much time. So that's why people just come up with this notation over here. Okay, but now I think I don't remember if I actually have a great example for you guys, but they're not really that many hard examples I can give you, or challenging ones. They're all kind of natural, I think. But sure, let's take this one. Let's take this one. it's all about practice, really. I can just give you, I'll just give you like two really not easy ones, but basically the hardest you can get with what you've learned today. And then I'll let you solve them, and then depending how everyone feels, I'll give you the roadmap and maybe even start a little bit of the next. But integral from -2 to 4 of x to, all right, x to the second over 5 plus 1 over that's not put it there. Okay, plus 1 over x squared. I'm fine with this. Plus 2x plus 1. Something like this. Like this is literally, I don't really see how you can get something more complicated than this. Yeah, that's fine. And since I made it a little bit longer than I intended, I'll just leave one for you guys. Okay, so just try to do your best on this one. I'll give 2 minutes. And let's see afterwards how everyone's feeling about it. If you got to the numbers part, I'm not really interested in knowing the exact answer. Just FYI. Okay. All right, guys, I'll assume everyone kind of went through it or at least struggled a little bit on it. So what I'm gonna do is nothing really special. I'm just gonna split it, probably take the constants out, and then plug in the values. So pretty natural, right? So I'm just gonna split it first, which I think is pretty good idea, at least for now. So I split it. Cool. Now, constants out. You don't need to, but I guess for me it makes it easier, at least now since I'm not acting too smart, so makes it easier for me. Okay, and now let's see. 1/5. What's the primitive, or what do I need to take a derivative of to get x squared? Is x to the third over 3 from -2 to 4 plus what do I need to take a derivative of in order to get 1/x squared? 1/x minus, so plus minus 1/x between -2 and 4 plus 2 for x. I need to get x squared, so x squared between -2 and 4 plus x between -2 and 4. Everyone did something like this, got something similar? Yeah, cool. Now, for computation, since we're already here, I guess I can do a fast computation. And what I meant is I'm not interested, even on the exam, if you get something like 5, if your final answer is 5 ln of 2, I'm just giving a complete example. Yeah.
Or the term there is meant to be this x squared. If you're raising the x by 1 and then dividing by 2.
Oh, of course. Yeah, I forgot. Oh, completely. I forgot to put it a 2 here. That is completely right. Thank you. Yes. Okay. So on the exam, if your final answer looks something like this, okay, I'm just giving a pure example. Do not plug in the calculator to tell me that this is equal to, I don't even know, something, okay? Do not plug in the calculator here, because nobody, like, when we're grading, we are expecting to see this result, okay? If you're plugging in and telling me that this is equal to something, what I'm gonna do is I'm gonna plug in myself this and see if it's actually that. So that's why we're gonna have a discussion, I guess, when it gets closer to the exam, but be really careful where you're using your calculator and where not. Try to be smart about it. And I'll show you here where I would use a calculator where I would not use a calculator. So just plugging in the numbers. 1/5, 4 to the third, that's 64 to the power of 3 minus -2 to the third, that's -8/3 plus this is -4, then it's minus, this is a little bit trickier, I guess. -1/-2. I think I did it correct. I hope at least. Plus, this was correct. This is 4 to the power of 2 minus 2 to the power of 2. Plus 4 minus -2. Now, if you had this, I guess you could, if you're really fast on the calculator or something, I guess you could plug in the calculator to see what this is equal to. I personally was a terrible calculator user, so I would never plug in calculator here. I would just compute it and let me show you what answer I would leave it to. So I'll compute this part over here, and this gives me 72 over 15. This is minus that's minus 3/4. This is 16 minus 4, 12, plus 4, 14, plus 2, that's 18. I think 16 minus 4, 12, plus 4, yeah, I did it correct. Okay. And realistically, I would much appreciate this answer rather than giving me the zeros for this. Okay. I hope I did the math correct here, but I hope the fractions are correct. But again, if on an exam, if you leave the answer as this, as opposed to telling me that this is going to be equal to this is equal to 3, 4, 6, 4. Like telling me this is like 21.3 something, I think, I wouldn't care about that. Okay. Just to give you an example where calculator can be useful and where it can be bad. In this case, I'm fine. In this case, I think it's terrible to use. But I hope after this example, everyone is kind of okay with what they have to do on these type of integrals. Makes sense for everyone. Now, let me show you how we are on the roadmap of integrals. So I guess roadmap. You don't even need to write this necessarily, but you can if you want. Oh. Because I'm not gonna teach you anything, at least not in what I'm gonna write here. So the roadmap was kind of define integrals, which we did. Show you the simple integrals. Slash methods with separating and taking the constant out. So we did this as well. And now we have to do the two last parts, which is the integration by parts. Which is the equivalent, I don't know how to write, but is the equivalent for the multiplication when you divide a product for the when you differentiate a product, equivalent to the differentiating product. Yeah. It's basically this, but applied to integrals. You know, and when I mean differentiating product rule, I'm talking about derivative of f of x times gx over dx. Okay. Basically, this rule is gonna give us a new method for solving integrals, which is gonna be called by parts. I personally would not be worried about this because whenever you have to use integration by parts, it's gonna be so standard. Like they're only like it's very often used, but the situations where we have to use it are so telegraphed that you're gonna see them from a mile. And then what I believe is the hardest and I guess the most finesse is substitution. And I'm gonna make a comment here on the substitution. If you think you're really, I mean, not smart, but if you think you have like this, you're very creative and everything, you can probably do a better solution than me or everyone here, because substitution is known for just having, if you have a bright idea, you can basically finish the problem in 2 lines, and everyone is gonna still be working 2 pages. So this is a very cool method as well. I think it's the coolest, but you know, it's the hardest to use at its fullest. Now, I guess since we have 15 minutes, I can give you just like a short dive into the integration by parts, but we're gonna do that Tuesday. I'm gonna repeat everything I'm saying now, and we're gonna actually start working with some cases. But the integration by parts. Okay, let's write the main idea. Derivative. I need to check. Derivative of f of x, g of x, dx is equal to, you know, product of f prime g f prime of x, g of x, plus f of x, g prime of x. Right? That's just the product rule. Now, if these two are equal, then if I integrate both of them, no, that's not. What is happening? I can't draw an essay. Okay, if I integrate, if they're equal, then if I integrate them, they're still going to be equal, right? So d of x here, d of x here. Everyone cool with that? Just like differentiating or just like raising the power, same concept. If they're equal, I can integrate them. They're still going to be equal. Yeah, of course. Yeah, that's my next step. But before that, I wanted to draw your attention here. I am taking a derivative of the product, and then I'm integrating it. Remember when I said integrating and derivating are basically the opposite factors? So this thing is just f of x times gx. Right. If I wasn't clear, let me just say it again. Remember when I drew the x squared 2x, and I said if I go from x squared to 2x, I'm derivating or differentiating. Differentiating. And if I go back, I'm integrating. Well, here, from f of x times g times g of x, I'm differentiating, and then I'm integrating. So I'm going once, and then I'm going back. So that's why I'm just have the original thing. Okay, think of it as flipping a fraction, or just putting a minus in front. Just I hope that makes sense. I'm not just ask me after that, but after this, as someone said, just split it. So I get integral from f prime of x, g of x, dx, plus integral f of x, g prime of x, dx. And this is what is called the by parts method. And I'm gonna show you all about it next week. Disclaimer: this also works for definite integrals, so I could have a, b, and from A to B here. Okay, so this also works for definite integrals. But I'm gonna show you, and we're actually gonna do, so this is all the theory that is for integration by parts. There's nothing more I can show you in terms of theory. So next week, probably for 2 hours, we're probably just gonna do examples of this. Because I think you do require a little bit of skill or observation to see how to apply it, right? Because it looks ugly. Let's agree on this. It looks ugly, especially when you have to apply it. So, but I'm gonna show you how to do it. It's actually easier than it looks. Okay. But that's, I guess, all for today. So yeah, 10 minutes early. I'm fine with that.